So today we are talking about some subspaces. Last class we talked about vector spaces and kind of came up with an idea of what does it mean to be a subspace. And today we're going to talk about some specific subspaces related to vectors and then also, or to matrices, and then also, of course, generalizing beyond that as we have been lately with vector spaces. So first off, let's just consider this problem. So let's say we want to solve this equation ax equals 0 for this matrix A. So set up the augmented matrix. Oops. Change colors there. There we go. Okay, so set up the augmented matrix. So -3, 6, -1, 1, -7, 1. You don't need to hear me saying the numbers. You can see them. Oh, I'm sorry, I wanted to augment it that way. 0, 0, 0. Okay. Okay. I'm going to switch the first and second rows. Come on. Okay, switch first and second rows. So 1, -2, 2, 3, -1, 0. Okay. Top row I leave alone. Next row, multiply the top row by 3 and add the second row. So this will be 5, 10, -4, 0. Okay, multiply the top row by -2 and add the bottom row. So 0, 0, 1, 2, -2, 0. Okay. I'm going to switch the second and third rows. I feel like I probably should leave myself more space, but oh well. Okay, top row, leave alone. Second row is fine. Okay, multiply the middle row by -5 and add the bottom row. I get 0, 0. -5, 6, 0. Okay. Bottom row, I'll make new 1. Okay, use that to clear out the top. So and then finally the bottom row is 0, 0, 0, 0, 1, 0. Middle row is fine with 0, 0, 1, 2, 0, 0. Top row. So multiply the middle row by -2 and add the top row. I get 1, -2, 0. -1, 0, 0. Finally, what does this tell me? This tells me that x1 minus 2x2 minus x4 is equal to 0. X3 plus 2x4 equals 0, and x5 is equal to 0. Which I can rewrite as, so x1 is equal to 2x2 plus x4. x2 is itself. x3 is -2x4. x4 is itself, and x5 equals 0. I bet you thought I wouldn't space that, didn't you? Okay, so finally, my general solution is, so it'd be 2, 1, 0, 0, 0 times x2 plus, that should be a 4. 1, 0, negative 2, 1, 0 times x4. Okay, I got a little bit ugly there, I apologize. But basically, our solutions are the linear combination of these two vectors. Okay. This is a problem we've already done before, so this is not the new stuff, but we're going to build off of this. So every single solution to this, remember this is called a homogeneous equation because the whole thing is equal to 0. Every single solution to this homogeneous equation can be written as the linear combination of these two vectors. Call these v1 and v2. Okay? Another way to say that is every solution to this homogeneous equation is in the span of v1 and v2 because they are all linear combinations of v1 and v2. Okay. Well, the set of solutions to the system form a subspace because this set is the span of vectors, right? We said last class that any span of two vectors in some vector space forms its own subspace. So because we have the span of these two vectors, this set of solutions is itself a subspace. And in fact, we have a name for that. The null space of a matrix, which we would write null A, is the set of solutions of the homogeneous equation AX equals 0. Now, let's remember that to be a subspace, couple things have to happen, but one of them is it has to include the 0 vector. Okay, so keep that in mind. A subspace has to include the 0 vector. So first of all, we can write the null of A. In fact, if we want to, we can even write that. Nope, that's an M. Null of A equals. Okay, so that's one way of expressing it. Just the null of A is the set of all X that are solutions to the homogeneous equation. This only works for the homogeneous equation, right? It does not work for the non-homogeneous because if we're solving the non-homogeneous, where the right side is some other vector b, it might not include the 0 vector, right? The trivial solution, the 0 vector, might not be a solution to the non-homogeneous. So this only works for the homogeneous equation. We call that the null space. Also, keep in mind that if we're solving the non-homogeneous equation, there's always the possibility it's inconsistent. There's always the possibility there's no solution. Whereas when we solve the homogeneous equation, there's always, at a minimum, the 0 vector works. It might be the only solution, but there is always at least one solution. Okay, so as an example here for this matrix, let's determine if this is in the null space. Well, we could go through and describe the null space, and we can go through and find the solutions to the homogeneous equation, etc., etc. Or we can realize that if it's in the null space, it's a solution to this equation. In other words, we can basically just ask the question, what is A times U? If A times U is 0, then it satisfies the homogeneous equation, and therefore it's in the null space. So A times U, so A is 1, -3, -2, -5, 9, 1. Use the vector 5, 3, -2. If I multiply these, I'm going to get 5 minus 9 plus 4. And then, I only need 2 spots. -25 plus 27 minus 2. And the first one is 0, the second one is 0. So, yep. So U is in the null space. Okay. So that's our first special subspace. Okay. Now, another description of the null space, consider a linear transformation. Okay. So a linear transformation basically says take any matrix or any vector x, and it's transformed into a new vector a times x, right? Whatever that happens to be. Well, if we're solving the homogeneous equation, we are only interested in the vectors where the result of this product is the zero vector. In other words, the null space is the set of all vectors that are mapped to the zero vector. Okay, it's a set of all vectors that when you multiply a times x, the result is the zero vector. Okay, so just something to consider. Okay, there is no obvious relation between the entries of A and the vectors of the null space of A, okay, or a spanning set. I guess it's possible you could look at a matrix and maybe come up with where the pivot points are going to be. That's a possibility, I guess. But there's no way to look at a matrix and just right away know, oh, yep, that's the, here are the vectors that make up the null space, or that span the null space. There's no way of doing it. The only way is to actually do the reduction like we did on the last example. Now, let's consider a different vector space, though. There's another special vector space. There are much more obvious connections. Another subspace which has more obvious connection, there should be a comma there, is the column space of A. Okay, so now this is a new definition. The column space of A, which we're going to denote col A, is the subspace that is the span of the columns of A. So now we're going to take all the columns of A and we're going to say, okay, create a new space that is the span of these columns. Fine. So it's a description. The description is all vectors that are the linear combination of those columns. Well, if we define A as just made up of those columns, so A1 is the column, A2 is the column, then a vector B is in the column space if B is a linear combination of A1, A2 up through AN, right? So B is a linear combination of those columns. Well, that's just another way of saying that B is a result of A times some matrix, right? If these x1, x2 up through xn, if those are the weights in this linear combination, put those all together, call that the vector x. Basically, B is in the column space if B is the result of A multiplied by x. Basically, if B is the output for some x, right? If we're looking for those weights, those x1, x2 up through xn, that's basically asking the same question. Hey, what is x? Right? Solve for x in this equation. So basically, for the linear combination, x goes to ax, or linear transformation, I should say, the column space is the range. The column space is the set of all vectors B that could come out of multiplying A by any vector at all. Okay, that's the idea. Basically, the column space is the range. Okay. Now remember, there's a difference between range and codomain. Remember that the codomain is basically what space are you mapping into, right? If you're mapping into R sub n, that would be the codomain. But the range would just be all the vectors in Rn that actually result from this product. Okay, so again, just a real quick reminder, if we have, here's our domain, and here's our codomain, we have a bunch of different points in here, they're each being mapped over here somewhere. Each of these points is in the range, because each of them actually has something mapping to it. But the codomain might have other entries that do not get mapped to. So the range is the entries that actually get mapped to, and the codomain would be basically everything in that set, even if some of them don't get mapped to it. Another example would be, what if you had the square root function? F of x equals the square root of x. So certainly, so the codomain would be all real numbers, right? Where if you plug in an x, you get back a real number. But the domain, or I'm sorry, but the range would just be that y is greater than or equal to 0. Right? The codomain could be all real numbers, but this function doesn't map to all real numbers. It only maps to numbers that are 0 or greater than 0. So that if I'm repeating stuff from earlier in the course, but it's worth just reminding ourselves. Anyway, okay. So let's find a matrix A such that W is the column space of A. Okay. So W is the set of all matrices that look like this, or all set of all vectors that look like this. And so I'm looking for a matrix where the columns of A span all of W. Yes, that's what I'm looking for. Now let's notice that the entries in W here are one vector, 6, 1, 0 times A. Oops. Nope. There we go, times A. Oh, I missed the 7, I'm sorry. So 6, 1, negative 7 times A, and then negative 1, 1, 0 times B. Okay, so we're looking for all the vectors that are like that. Well, it's worth pointing out that this is the span of those two vectors, 6, 1, negative 7, and negative 1, 1, 0. Okay, the span of these two vectors is the set of all vectors that are linear combinations of these. Well, that's what W is. W is the first vector times any number A, and the second vector is any number times B, or any number times, yeah. So we want the span of this. Well, that means that this is the column space of A, capital C, column space of A, where A, the columns of A are just those two vectors, 6, 1, negative 7, and negative 1, 1, 0. Okay, so that's just, we're looking for vectors that span the entire set W, and those vectors are going to be the columns of my matrix A, because the column space is the span of those columns. Okay. All right, consider this for a moment. Let's say that A is a 4 by 3 matrix. Okay, so we want to know what would be the dimensions of or the column of A, column space of A is the subspace of what, R sub what, and then same for the null. Okay, fine. So we have a 3 by 4 matrix, and let's consider this X equals something over here. Now again, if this is a 3 by 4 matrix, that means that X is going to have to be a 4 by 1 matrix in order for those sizes to match up. And if we do that product, the result's going to be a 3 by 1 matrix. Now keep in mind the null space, I'm going to start with part B here for a second. The null space is the set of all vectors that map to the 0 vector. In other words, the null space assumes that the right side of this equation is the 0 vector. And the null space is made up of all the x's. So notice that all the x's are 4 by 1, so the null space has to be made up of entries, made up of vectors from R of 4. Likewise, the column space. Well, the column space represents all the different possible outcomes we could get if we pick different x's. So the column space is all about the outcomes. So in this case, that would be a 3, because when we do this product, the outcomes are vectors that are 3 by 1. So that's it, just thinking about the different dimensions here. Okay, for this vector, or for this matrix, determine if U is in the column space. Okay, so again, we are basically asking, is this vector an output if we picked some x? Another way of asking that is, find x that results in A times x equaling this vector U. So we're going to solve this equation, AX equals U, we're going to set up the augmented matrix. So 1, -3, -2, 5, -5, 9, 1, 3. And by the way, determine if it's in the column space. We don't even need to find the solution. We just need to know, is there one? We need to know, is this system consistent? If I multiply first of all, leave the top row alone. If I multiply the top row by 5 and add the bottom row, I get 0, -6, -9, 22. The numbers don't really matter. The important thing is it's consistent. We have the pivot point on the bottom row is not all the way to the right. There is a pivot point here and here. This is consistent. Therefore, U is in the column space of A. That's it. Okay, there is a solution. We didn't find it. I don't actually care what the solution is, but it definitely does exist. Okay, let's see. How about this one? Okay, for A is this matrix. Find a non-zero vector in column space of A and a non-zero vector in the null space of A. Okay. Well, first of all, the column space of A is the linear combination of these three vectors. All I need to do is find one vector that is a linear combination of these. In fact, even easier than that, I can just pick one of the vectors. So one vector in the column space of A, okay, well, how about 1, -5? Done, okay? Any linear combination of those columns is a good answer. Well, any non-zero linear combination is a good answer. So I just picked one of them, whatever. Okay? You could have picked any of the other vectors. You could have added them together. Who cares? Now, a non-zero vector in the null space, as I said earlier, this time we really do need to actually solve that homogeneous equation. Okay, so again, top row is fine. Oh, these numbers look familiar. Okay, so we get 0, -6, -9, 0. And this time we really do want to solve this out. I'm going to divide the bottom row by 3, by -3. 1, -3, -2, 0, 0, 2, 3, 0. Okay, this is not fun. That's okay. 1, -3, -2, 0. Okay. You know what? I'm going to change that last one. I'm going to divide everything by -6. I'm not excited about the fractions, but it is what it is. Okay, so I'm getting 1 and then 3 halves. Okay. So now if I multiply the bottom row by 3 and add the top row, oh, I got to change the top row now. Okay, so this 0, 1, 3 halves, 0. And so multiply the bottom row by 3 and add the top row. I get this is 0, and this is 3 halves, which is, or multiply by 3, so 9 halves, 4.5, 2.5, so that's 5 halves. Okay, and so this tells me that x1 plus 5 halves, x3 equals 0. x2 plus 3 halves, x3 is equal to 0. So x1 is equal to -5 halves, x3. x2 is equal to -3 halves, x3. And x3 equals x3. So all of my solutions look like this. -5 halves, -3 halves, and 1, all times x3. So I need one vector that's in the null space. I could pick the simplest one, I guess. I could pick -5 halves, -3 halves, and 1. If I wanted to really avoid fractions, I could pick I could pick x3 to be any number that I want. I picked 1. Make it 2. Then your vector is -5, -3, and 2. Okay, that works fine. You can pick x3 to be anything you want it to be. Okay. These two vectors are quite different, though they are going to be connected, and we'll talk about that next class. But the null space, again, if A is an M by N matrix, we saw already the null space of A is in Rn, whereas the column space is in Rm. The null space is implicitly defined. That is, you're only given a condition AX equals 0 that vectors in null A must satisfy. This just means you can't just look at it and know what the answer is. You actually have to go through and do the work. Actually, that's what part 3 says. Sorry. It takes time to find the vectors of the null space where all operations are required. Whereas the column space of A is explicitly defined. All you're doing is working with the vectors, the columns. Number 4 here, there's no obvious relation between the null of A and the entries, whereas there is an obvious relation between the column space. It's the columns. The typical vector V in Rn has the property, typical property. Okay, so yeah, number 5 there, null space solves is solutions to the homogeneous. The column space is vectors that are resulting from A multiplied by X. So they're the outputs. Given a vector, it's easy to tell if it's in the null space. Just multiply and see if you get 0. Given a specific vector, it takes some time. Okay, I'm not at number 6 here. It takes some time because you actually have to solve, and we saw an example earlier. We saw that example earlier. To see if it's in the column space, we had to actually solve the equation, the system. The null space might be just the 0 vector. Okay, and so the trivial solution might be the only one. It is possible that the column space is all of Rn if every vector in Rm is an output. Okay, we have seen examples of that in the past. Okay, cool. And then number 8 there, the null space is the 0 vector if and only if it's a 1-to-1 transformation. Remember, the null space is all the vectors that map to 0. Well, if there's only one vector that maps to 0, that's 1-to-1. And the column space is the entire R to the M if it's onto, right? Onto means the entire codomain is the range. And so if the column space makes up the entire Rm, that means that this is onto, that everything in Rm is an output. Okay. When considering more abstract vector spaces, okay, so now moving beyond Rn and Rm, when we're going more abstract here, we discuss linear transformations rather than matrices, right? We saw that linear transformations can be expressed as matrices, but when we talk about more abstract vector spaces, we can only talk about linear transformations because now the idea of a matrix may not make any sense. So first off, a linear transformation. Okay, we haven't actually talked about that for vector spaces yet. A linear transformation T from a vector space V to another vector space W is a rule that assigns to each vector X in V a unique vector T of X in W such that, okay, this is all very confusing. X is in the input, T of X is the output. Okay, just like any other function. 2 conditions. First of all, you have to be able to split up adding. Second of all, you have to be able to pull out coefficients. Okay, we've seen that, right? We've every time we did derivatives, right? That was we had these 2 properties. So actually, we're going to talk about that in just a minute. But that's these are called the linearity properties, and we certainly saw that this was true where the transformation is matrix multiplication. But we're generalizing that a little bit. So any transformation has to follow these 2 rules. Okay, now a couple more definitions here. The kernel is the subspace that is mapped to the 0 vector. Okay, so the kernel of some linear transformation is all the inputs that map to the 0 vector. Well, if the T happens to be a matrix transformation, the null space is the kernel. Because that's all, again, the null space is everything that maps to the 0 vector. So that's the name for that. The range of T, right, it's the same word range we've talked about before. The range of T is the subspace of W of all vectors of the form T of X for some T. The range is all the possible outcomes, all the possible outputs. Again, we have a name for that. If T is the if Matrix transformation, then that is what we call the column space. Okay. An example of an abstract linear transformation, right, that isn't just matrices, would be the derivative. Okay, so a linear transformation takes something and changes it into something else that has those linearity properties. Well, we saw that that was true for derivatives. So if I had, maybe if my vector x was, I don't know, how about secant x, or secant of t, I'll pick the other better. Then if my linear transformation is the derivative transformation, then the output would be secant t tangent t. Okay, but because the derivative, we can split it back and we can pull out coefficients, the derivative is a linear transformation. One notation we're going to use here, C of AB, we're going to define that as basically all the continuous functions on the closed interval from A to B. So just when that notation comes up, we know what that means. So C just represents continuous functions. So consider this situation. Let's define the linear transformation T. Now we're going from P2. Remember, P2 was all polynomials of degree at most 2. So it's polynomials of degree 2, a degree 1, or even the constant polynomials. And we're mapping them to R squared. Okay, so R squared is vectors, right? It's 2 by 1 vectors, and so we're defining it as, I lost a parentheses here. We're defining it as the transformation of polynomial P is the vector where the top entry is the value of P at 0, and the bottom vector, bottom component, is the derivative of P at 0, and we want to find the kernel of T. Okay, well, again, kernel of T means find all vectors that map to the 0 vector, 0, 0. Well, in this case, that means we're looking for a polynomial where P of 0 is equal to 0, and also P prime of 0 is equal to 0. Remember, P is in P squared here, P2, I should say. So we're looking for all polynomials. We're looking to describe all polynomials whose value at 0 is 0, and also whose first derivative at 0 is 0. The only ones I can think of would be the set of all P that is a constant times x squared. Right? Plug in 0, you get 0. Take the derivative and plug in 0, you also get 0. So, and then where A can be any real number. So as long as we pick a polynomial that's just a constant times x squared, right? No x term, no constant term, then it will then transform. It'll result in, if doing this linear transformation, it will result in the 0 vector. All right, next up, let's talk about linear independence. A set of vectors v1, v2 up through vn is linearly independent if there exist constants c1, c2 up through cp that are not all 0, such that this combination is 0, and this equation is called the linear dependence relation. This should not be anything new. We've done this before. The only difference is that we did it with vectors in Rn, and now we're talking about more generalized vectors. A set is linearly independent if the coefficients if setting the coefficients equal to 0 is the only way to make the whole combination be 0. Again, this is not new. This is stuff we've already done. Now, some reminders. If a set is dependent, one of the vectors can be written as the linear combination of the others. Okay, so if this relation was true, I could solve for example, v1. Right? I can solve for that vector. So then V1 would be a linear combination of the others. And then as we saw before, the vectors in when we saw this before, when we talked about this linear independence, the vectors in Rn, the vectors were in Rn, right? That's what we worked with before. And we looked at the equation Ax equals 0. Right? We were basically solving the equation Ax equals 0 and asking the question, do we get anything other than the trivial solution? Right? If we get only the trivial solution, then they are linearly independent. For abstract spaces, of course, we can't rely on that, right? There is no matrix multiplication. So consider P, which is the set of P. I don't remember if we've done this before, but P is just the set of all polynomials of any degree. And let's determine if these 4 vectors are linearly dependent. Well, let's notice that P4 is equal, if I FOIL it out here, it's t squared plus 6t plus 9. Please notice that that is equal to 1 times P3 plus 6 times P2 plus 9 times P1. In other words, this is my linear relationship, or my linear dependence relation. Because P4 can be written in terms of the others, we would say that this is a dependent set. Okay, it's a dependent set of vectors. Let's consider this. In C of 0, 1, again, that's the continuous functions on the interval from 0 to 1. Let's determine if these 2 functions are linearly dependent. Now, it's only 2 functions, and so I believe we talked about this briefly, but basically 2 functions are linearly dependent. Well, that would be asking the question, basically, could I do A times cosine t plus B times sine t and get the result of 0? Well, that would be the same as saying the cosine t is equal to negative b over a times sine t. Well, and that is certainly true for some values of t, but not for all, right? We want to know, is there some relationship where this is true no matter what t we pick? So for that reason, this is linearly independent. Because there is no dependence relation, or more specifically, because there are only 2 functions, one of them is not a constant times the other. That's the only way they could be dependent. Now let me change it up here a little bit. Now let's show that this is linearly dependent. By the way, notice the change in directions here. This time we're told it's dependent. We just have to show that that's the case. So I'm going to work on that sine of t plus pi over 4. And let me see here. This is the same. Let me see if I remember my basic trig identities. This is sine t cosine pi over 4 plus cosine t sine pi over 4. And so that's radical 2 over 2 times sine t plus radical 2 over 2 times cosine t. But notice, if I call this, say, V1, V2, and this over here is V3, notice what I'm saying is that V3 equals root 2 over 2 times V1 plus root 2 over 2 times V2. That's a dependence relation. Okay, so therefore these are dependent. Okay. So the question now becomes this. What if we have a set of vectors, whether they're dependent or independent, it doesn't really matter. What if we have a set of vectors? Now, we know that the span of any set of vectors is a subspace. Okay, so let me say that again. The span of any set of vectors is a subspace. In this example, the span of cosine t, sine t, sine of t plus pi over 4 is a subspace. And the span of any vectors is a subspace. Well, but here's the thing. Because this was linearly dependent, I can just cross it out. and it wouldn't change the subspace, right? I can take out any, if a vector is dependent, is a linear combination of the others, I can just take it out, and that won't change the subspace. I won't lose any members of that set. And so now the question becomes, well, okay, so I guess the question is, what do we call that, right? When we find not just the span of a set of vectors, but it's the span that also happens to be independent, where we've taken out any dependent elements. So let H be a basis, let H be a subspace of a vector space V. So a set of vectors B in V, so some set of vectors in this vector space is called a subspace if the vectors in B are linearly independent, and if the vectors in B span H. This would be considered the most efficient way to define the subspace H, right? Every subspace has some defining set of vectors that span it. A basis would be the smallest such set, okay? And yeah, so let's play around with that a little bit. So we have these three vectors, v1, v2, and v3, and we want to know if they form a basis for Rn. I'm thinking that this should actually be R3. Because they're all entries in R3. Now, first of all, and I believe we've already talked about this, in order to, let me see here, in order to find all of R3, we need three vectors. So we got the right number of vectors. The only thing we don't yet know is if they're linearly independent, right? So that's the one thing we really do have to check. So there are different ways to do this, right? We basically want to see if these are linearly independent functions or independent vectors. There are some options, right? We could, well, let's do one thing first here. Let's create matrix A that's made up of these columns. So 3, 0, negative 6, negative 4, 1, 7, negative 2, 1, 5. Okay. We have a whole ton of stuff we could do here. We could see if we have a pivot position in every column and every row. Right? We certainly did that plenty in the last couple chapters. We could use determinant. We could find the determinant and see if the determinant is non-zero. Okay, that would totally work here too. We really have a lot of choices, and what you do is all totally up to you, because we have that whole big long list of it was the invertible matrix theorem. Basically, we have this whole list of things that are equivalent to a matrix being invertible, and so go down the list. Why don't we do determinant? We haven't done that much. So the determinant of A. So I'll do 3 times its smaller matrix minus 0 times who cares plus negative 6 times its smaller matrix. And so I'm getting 3 times 5 minus 7. I wrote 4 for some reason. 5 minus 7 plus 0 minus 6 times negative 4 plus 2. So I'm getting negative 6 plus 12. I'm getting 6, but more importantly, I'm not getting 0. Because I didn't get 0, that means that the vectors are independent. Which means that the span of v1, v2, v3 is equal to R3. It's worth mentioning, if I were to add another vector to that set, the span would still be R3. The difference is it would not be a basis, because then if I were to add like a v4, and you pick any vector you want, doesn't really matter, 5, 1, 7, whatever, just make a number. If I put that in, the span of those 4 vectors is still R3. The difference is it would not be a basis anymore, because by putting in that extra vector, now it's no longer independent. Okay. Okay. If we look at the columns of IN, we call that the standard basis for Rn. Those of you who do physics and when we're talking about vectors, I know some people were talking about I, and K. This is the same thing. I just have different names for them. But in R3, the standard basis vectors are E1, which is the first column of I, E2, which is the second column of I, and E3 is the third column of I. Okay, so this would be what we call the standard basis. Basically, it's the simplest one, but as we saw in the last example, there are lots of different ways to write a basis for a vector space. If we're considering Pn, the standard basis, again, just the simplest, most basic one would be the one that allows us to define each term of that polynomial. So 1t, t squared, all the way up to tn, we would call that the standard basis for Pn. Okay, these vectors are dependent. Okay, so I'm already telling you that these are dependent. If H is the span, let's identify a basis for H. I'm going to solve the equation. So I'm going to take those vectors and put them into a matrix here. So A is the matrix. First column is 1, 2, 3, 4, 5, 6, 2, 1, 0. Apparently, I was not very creative when I wrote these vectors. And I'm going to solve the equation AX equals 0. Okay, and I'll show you why I'm doing that in a second. Augmented matrix. Okay, 1, 4, 2, 0. Multiply the top by -2 and add the bottom, or add the second one. -3, -3, 0. And then top one by -3 and add the bottom. At 0, -6, -6, 0. Got 1, 4, 2, 0. Middle row becomes 0, 1, 1, 0, and the bottom row becomes all zeros. And then finally, multiply the middle row by -4 and add the top. And so we get, all right, let's see here. So we get x1 minus 2x3 equals 0, x2 plus x3 equals 0. And so x1 is equal to 2x3, x2 equals -x3, and x3 equals x3. So all of my solutions are x equals, let's see, it'll be 2, -1, 1 times x3. Okay. So this tells me that 2x1 minus x2 plus x3 is equal to 0. I'm sorry, that's not what I meant to say. 2v1 minus v2 plus v3 is equal to 0. Our solving for x basically finds the weights, and if we were finding where a times x equals 0, we're finding the weights that cause this relationship to be equal to 0. This is my dependence relation. More specifically, I could say v3 is equal to -2v1 plus v2. In other words, v3 is dependent on the other two. So the basis that I'm looking for would be, would be the span of only the first two vectors. Because we don't need the third one. The third one is a linear combination of the first two. Now, because we're told that they are dependent from the very beginning, I know that I'm going to be able to throw out at least one of them. The only reason that I kept going through this whole process was to see if I can throw out two of them. It's completely possible that you get a dependence relation where maybe, I guess, let's put it this way. In this case, we had one free variable because there was one column with no pivot position. We could have had a matrix with two free variables, in which case, I guess I'd have to think about it, but I believe in that case we would only need one vector, the span of just that one vector as our basis instead of two of them. So anyway, it was worth going through that process. Okay. Let's see here. Okay, so let's consider, a basis is a, what does that say? A basis is a spanning set that is as small as possible, right? So basically that's what we've been saying. Okay, let's find the basis. So again, we've determined that this entry was the one that was dependent on the others. So H could be the span of just the first three, 1, t, and t squared. Okay. In this case, we found that these were independent, so this was our basis that we're looking for this time. Okay. So, you know what? Let me rewrite this just a little bit. The basis that I'm looking for is this set. So here, the basis, they're already independent. So the basis would just be the cosine t and sine t. And in this case right here, again, we found that this vector was dependent on the others. So here the basis, we can throw out the one that was dependent. And so the basis would just be the cosine t sine t. So in this case, it looks like, it's definitely, these are actually the same set. These are the same subspace. Okay, back to null space and column space for a second. We previously found vectors that span the null space of a vector, right? This would be the basis of the null space of A. So if the null space is the set of all points that, or the set of all vectors that map to 0, we've already seen examples, we've already worked through examples where we found the vectors that we're looking for. Okay, so as a simple example here, if we want to find the basis of this, the null space of B, the top row tells me that, let's see, x1 plus 4x2 plus 2x4 is equal to 0. And then x3 minus x4 is equal to 0. And then x5 is equal to 0. So that's not what I wanted. So x1, come on. x1 is equal to negative 4x2 minus 2x4. x2 is free, so it can be itself. x3 is equal to x4. x4 also is free, so x4 is itself. And then x5 is 0. So this means that all of our solutions can be written as, let's see, negative 4, 1, 0, 0, 0 times x1, or x2, excuse me, plus, let's see, negative 2, 0, 1, 1, 0 times x4. And so the basis that I'm looking for is the vectors whose span is being described here. So that would be those vectors, negative 4, 1, 0, 0, 0, and negative 2, 0, 1, 1, 0. So those two vectors form the basis for the null space. Of course, this was an easy example because it's already in reduced echelon form, but yeah, we got that. Okay, so turns out the pivot columns of a matrix form a basis for the column space of the matrix. So we know that the column space, well, for this matrix, we know that the free variables were x2 and x4 because those were columns that were not pivot columns. Turns out that if we're looking at the columns of a matrix, the columns that contain the free variables, or the columns that indicate the free variables, are dependent on the other columns. So that means that if we want a basis of the column space, that means we only want to look in the pivot columns. So let's find a basis for this column, for the column space of A, and here's A. Now the hint that we're given here is that this is row equivalent to the example from B from the last example. In other words, the pivot positions were this one, and this one. So the basis that we're looking for is the columns that had pivots. So that would be the first column, 1, 3, 2, 5. The second column, which is 0, 1, 1, 2. I'm sorry, the third column, that is. And then the fifth column was negative 1, 5, 2, 8. And the other two columns were the free variables, and so we don't need those. Those two columns would be linear combinations of the three I've already identified. Now, there's a really important thing that we have to be careful about. First of all, as we've already discussed, to find the null space, you have to go through and do all the row reductions. You have to reduce it to reduced echelon form. Right? That was the only option, the only way to do that. Column space, we didn't have to do that before. However, notice that to identify which columns to pick for the basis of the column space, we need to know what the pivot columns are. That doesn't mean you have to go all the way down to here, but at a minimum, you have to take this, you have to reduce it to echelon form. At a minimum, you have to identify what the pivot positions are, what the pivot columns are. So at a minimum, you would have to go through that work. But then the other really important thing to keep in mind is, yes, you have to identify the pivot positions. However, make sure that you use the columns from the original matrix A. Don't use the reduced versions. The column space is the span of the columns of A. When you start doing row operations, you're creating new columns. Don't use those. Reduce it to echelon form to identify the pivot columns, but then go back to the original matrix A to actually decide which vectors to use for the basis. All right, so notice that on here, we identified these the three pivot columns, but we went to the original matrix A to actually take those columns and use them to create the basis. I'm trying to say this in as many ways as I can because I want to make sure there isn't any confusion. Anyway, that is the end of the lesson. Thank you for listening and watching.